You open your phone for a quick check. Just 5 minutes maybe. Before you know it, an hour has passed. You're scrolling, liking, refreshing, as time melts in your hands. But it's not random. It's not accidental. This is not just your willpower slipping. You're inside an algorithm. One specifically designed to keep you there. Tonight, let's drift through the quietly disturbing world of how mathematics, psychology, and artificial intelligence come together to hijack your attention. A system engineered, line by line, to know you, perhaps better than you know yourself. And it starts innocently. When you open a social media app, what do you see? A video, a meme, a post from a friend, an ad, another video, another ad. You're not seeing this by chance. Behind the screen, a sophisticated algorithm is calculating, in real time, what you're most likely to interact with. It learns from your every tap, pause, replay, and swipe. But how? Most modern social media platforms, like TikTok, Instagram, YouTube, and Facebook, rely on something called reinforcement learning. This is a form of machine learning, where algorithms aren't given direct instructions, but rather learn through trial, error, and reward. If a video makes you stay longer, that's a reward. If a post gets you to click, another reward. If you leave the app, that's a punishment. And so, like a digital scientist, the algorithm keeps adjusting, refining, optimizing, until your behavior becomes predictable. This predictability is the goldmine. The more the system knows you, the better it can recommend content, and the longer you'll stay. But here's the unsettling twist. The goal isn't just to give you what you like, it's to stimulate your brain's reward circuitry, especially dopamine. Dopamine isn't pleasure itself, it's the anticipation of reward, the itch before the scratch, and social media exploits it masterfully. When you pull down to refresh your feed, like a slot machine lever, you're engaging in a variable reward schedule. Sometimes there's something exciting, sometimes there's nothing. This unpredictability is precisely what makes it addictive. It's the same principle casinos use in slot machines, the same behavioral loop that trains lab rats to press a lever hundreds of times for a random pellet of food. Except here, the reward is a like, a message, a piece of drama, an opinion that confirms yours, or a video you didn't expect to enjoy. Over time, your brain starts to crave the scroll, even when the content doesn't satisfy. It's not pleasure, it's habit. So what is the algorithm really optimizing? Not your joy, not your growth, not your well-being. It's optimizing for engagement, the measurable currency of your attention. The longer you're on the platform, the more ads they can show you. The more ads you see, the more money they make. And that's it. That's the incentive structure. An artificial intelligence, trained on billions of data points, is tweaking what you see to serve its goal, not yours. And the result? You start to feel anxious when you're not on your phone, restless, compelled to check. The silence becomes uncomfortable. This is what psychologists call a behavioral loop. Cue, action, reward, repeat. And it's no accident. Designers and engineers work hand in hand with behavioral psychologists to create sticky experiences. Things like infinite scroll, push notifications, autoplay, all exist to reduce friction, the effort required to continue using the app. The easier it is to engage, the harder it is to leave. But perhaps the eeriest part of all is this: you're not the only one being optimized, everyone is, which means the algorithm doesn't just respond to you, it responds to everyone else's behavior too. If outrage gets more clicks, you'll see more of it. If polarization keeps people talking, it'll amplify division. If misinformation spreads faster than truth, well, the algorithm doesn't care. It's not moral, it's not evil, it's just efficient. And that's the haunting beauty of it. A cold, indifferent system that reshapes human culture, emotion, and behavior, simply by optimizing for one thing: time. The longer you stay, the better it has done its job. And it never sleeps. So what can we do? Awareness is the first step. Realize that behind every tap is a machine watching, learning, and adapting. Recognize the urge to scroll not as a personal failing, but as a reaction to an incredibly powerful system. You are not weak, you are simply human, and the algorithm knows exactly what that means. Still, you can reclaim your time, you can set limits, you can pause, you can become mindful of your digital instincts, and in that awareness, you might find something radical: silence, slowness, boredom, the very things these platforms try to erase, because in those quiet moments, you remember what it's like to choose. Take a moment now, breathe in, breathe out, notice the stillness between thoughts. Somewhere, miles beneath your feet, the earth is shifting. Not in dramatic cracks or thunderous rumbles, not yet, but in slow, almost imperceptible movements. Plates grind, tension builds, and silence deepens. It's in that silence, deep within the crust, that scientists try to listen for something elusive, the numbers that might one day predict an earthquake. Tonight, as you lie still in your bed, feel the stillness of the ground below you. It seems solid, immovable, but beneath the illusion of calm, the earth is in constant motion. And somewhere, in that motion, we search for patterns. Earthquakes are among the most devastating natural phenomena, sudden, powerful, and often impossible to predict with precision. But that hasn't stopped us from trying. Let's begin with what we know. The surface of the earth is divided into large shifting plates, segments of crust that float atop the mantle like pieces of a cracked eggshell. These tectonic plates move slowly, just centimeters a year, but they don't move smoothly. Sometimes, they get stuck. Friction holds them in place, even as forces build up beneath. Over time, this stress increases, until suddenly, violently, it releases. The plates lurch, the ground trembles, and we call it an earthquake. The central question, the one that has haunted geologists and physicists alike, is simple: can we predict when this will happen? The answer, so far, is not really, but we can find clues made of numbers. Let's talk first about seismic patterns. When a fault, a crack between two plates, releases energy, it sends out seismic waves. These waves travel through the earth, like ripples in a pond. We detect them with instruments called seismographs, which record even the slightest tremor. Over decades, scientists have compiled vast databases of earthquake activity, and from that data, a few mysterious patterns have emerged. One of the most famous is the Gutenberg-Richter law, a simple but powerful equation that tells us small earthquakes happen frequently, large earthquakes happen rarely, and their relationship follows a logarithmic curve. That is, for every increase in magnitude, the number of earthquakes drops by a factor of 10. In other words, for every magnitude 6, there are 10 magnitude 5s, and 100 magnitude 4s. It's not perfect, but it's statistically consistent, and it tells us that earthquakes follow a kind of power law distribution, not unlike stock market crashes or avalanches. This mathematical shape, this distribution of frequency versus magnitude, hints at something deeper, that the Earth, like many complex systems, behaves non-linearly, that small stresses can build up invisibly until a tipping point is reached. This is where chaos theory begins to whisper. Small differences in the system, tiny, undetectable changes, can lead to wildly different outcomes. It means we might never predict the exact moment of an earthquake, but we can begin to estimate likelihoods. Another tool in the predictive arsenal is the study of foreshocks, smaller quakes that sometimes precede a major one. In some regions, scientists have noticed patterns: a small swarm of tremors, a quiet period, and then a big rupture. But here's the unsettling part: not all large quakes have foreshocks, and not all foreshocks lead to a large quake. The pattern breaks, the numbers become noise. Still, researchers continue to refine their models using something called statistical seismology. They analyze stress accumulation on faults using GPS data, satellite radar, and machine learning algorithms that sift through billions of data points, searching for weak signals, hidden correlations, and subtle shifts. One promising technique is called earthquake nowcasting. It doesn't predict a specific event, but it estimates the current risk level, based on how much time has passed since the last major quake in a given region, and how many small quakes have occurred since then. It's not a crystal ball, but it's a compass, a way to gauge pressure in the system. And yet, for all our measurements, our equations, and our models, there remains a quiet humility in earthquake science, because sometimes, the Earth simply doesn't obey. An area with no recent activity suddenly slips. A supposedly stable region rumbles to life. The numbers fail, and that's where this segment takes a turn, into something more philosophical, because earthquakes remind us that some systems are fundamentally unknowable in detail, even if they're predictable in shape. They remind us that uncertainty is not the same as ignorance, and that not all truths are expressible in formulas. Sometimes, the best we can do is listen to the silence, monitor the tremors, and wait. So the next time you hear of an earthquake, or feel one, know that beneath the surface was a dance of numbers, pressures, angles, fractures, faults, each with its own role in a story written in geologic time. And even in its unpredictability, there is pattern, there is mathematics, There is meaning. The Earth is not random, but it is vast, and the numbers that predict earthquakes, they are whispers, not declarations. Take a moment to reflect. Your bed is still, but the planet is always moving. You're standing in a sleek, quiet office lobby. It's early morning. You press the button for the elevator. A light chimes. Doors open. You step inside, alone, and are whisked away to the 27th floor. Simple, right? But hidden beneath this seemingly effortless moment is a mathematical dance of remarkable complexity, one that belongs to a branch of mathematics called queuing theory. Tonight, as you relax and let go of the day, let's take a slow, thoughtful ride into the strange elegance of how elevators, yes, elevators, use mathematics to move us efficiently through vertical space, often without us ever noticing. It all starts with a problem. Modern buildings have dozens, sometimes hundreds of floors. Thousands of people come and go throughout the day, in waves, not in steady streams. Mornings are chaotic. Lunch brings clusters of movement. Late afternoon becomes a slow trickle, and people are impatient. We expect the elevator to come quickly. We hate waiting. We dislike crowded cabins. We want to go up or down, and we want to go now. How can a building predict, manage, and optimize all these unpredictable, conflicting requests? That's where queuing theory comes in. The study of waiting lines. Queuing theory originated in the early 1900s, developed by Danish mathematician Agne Krag Erlang, who initially used it to optimize telephone networks. But today it's used in everything from hospitals to customer service, and yes, elevators. The basic idea is to model arrivals, service times and capacity, then use probability and statistics to make decisions that minimize wait time, energy use and congestion. Let's go back to that elevator. When you press the button, you might think it simply responds. A cabin moves to your floor, and that's that. But in most modern systems, especially in buildings with multiple elevators, there's something much more sophisticated happening. Elevators are controlled by dispatching algorithms, systems that decide which elevator should respond to which call, based on a constantly changing matrix of variables, where each elevator is headed, how full each one is, how many requests are pending, what time of day it is, even what the traffic has looked like historically. And all this is happening in milliseconds. Let's say 2 elevators are nearby. When someone presses the up button on the 10th floor, the system will estimate, based on past data and current positions, which elevator can serve the request with the least total disruption to all passengers. This balance is delicate. Too many stops, and the ride becomes frustrating. Too few, and wait times increase for everyone else. Some systems prioritize shorter individual waits. Others aim to maximize total throughput. It depends on the design goals of the building. In more advanced systems, especially in corporate skyscrapers and smart buildings, there's something called destination control. Instead of pressing up or down, passengers type in their desired floor on a screen before boarding. The system then groups people going to similar floors into the same cabin, drastically improving efficiency. Think of it like carpooling, but vertical. Queuing theory even allows buildings to adapt throughout the day. In the morning, when most people are going up, elevators are programmed to anticipate this. They hover near the ground floor, ready for incoming traffic. Around lunchtime, more elevators may idle near the middle floors. At 5 p.m, the system flips, prioritizing downward traffic. And in the background, all of this is being optimized continuously, often with the help of machine learning, which identifies subtle patterns. When do people tend to crowd the lobby? How long do they typically hold the door? Which floors have the most traffic on Wednesdays? The elevator becomes less like a dumb machine, and more like a living system, reacting to its environment, learning from the behavior of its users. But queuing theory doesn't just optimize elevators, it models human behavior. It takes into account arrival rates, service distributions, queue lengths, and even psychological factors, like the perception of fairness. For example, studies show that people are more tolerant of waiting when they're moving, even if it takes longer. That's why elevators often try to minimize idle time. A full elevator, slowly ascending, is less frustrating than waiting 30 seconds with no motion. There's even thought given to mirror placement inside elevator lobbies. Mirrors distract people from the wait, reducing perceived delay. This isn't math per se, but it's another way of engineering the queuing experience. So what does this all mean? It means that behind every elevator ride you've ever taken, there is a system, elegant, mathematical, often invisible, trying to serve you fairly and efficiently, based on principles that emerged from war rooms, call centers, and probability theory. Next time you step into an elevator, think about this. Somewhere, an algorithm predicted your arrival. It weighed your needs against dozens of others. It made a decision, quietly, instantly, to serve you, or someone else. First, and it will do it again. 1,000 times a day. Silently, we don't often think about elevators. They just appear, open, close, and disappear again. But in that silence, there's a whisper of math, of logic designed to manage the delicate balance between time, motion, and fairness. So next time you're waiting, maybe smile. You're not waiting alone. You're part of a model, a pattern, a quiet equation in the vertical life of the modern world. Take a breath. Feel the hum beneath the floor. You're in the system now, and the system is efficient. Imagine a soccer match under the stadium lights. The crowd roars. Players blur across the field. A ball arcs through the air in a perfect curve, as if guided by some invisible thread. But what if I told you that beneath the sweat, speed, and instinct, there's math? Every movement, every strategy, every angle, quietly governed by equations, geometry, and probability. Tonight we explore the hidden mathematics in sports, the unseen algorithms of human excellence, and how numbers shape what we call the beautiful game. Let's begin with something simple, the arc of a ball. When a footballer strikes the ball into the air, it follows a path called a parabola, a smooth curve defined by a quadratic equation. The speed, angle, and spin all determine its height and distance. Even wind resistance plays a role, subtly changing the trajectory. To the player, this is instinctive. To a physicist, it's Newton's laws in motion. And when the ball curves dramatically mid-air, like in a curling free kick, it's due to the Magnus effect. As the ball spins, it creates pressure differences in the surrounding air, causing it to bend, almost magically, toward or away from the goal. This isn't guesswork. It's physics, performed in real time by the body, the brain, and the environment. But it doesn't stop at movement. Let's shift to basketball, a sport that's surprisingly rich in geometry. Picture a three-point shot. The best players release the ball at an angle between 45 and 55 degrees, with a rotational backspin, and enough height to let the ball descend nearly vertically. Why? Because a steeper descent increases the margin for error. A shallow shot has a narrow entry window. A high arcing shot gives the ball more room to fall cleanly through the hoop. Engineers have modeled this. Mathematicians have simulated optimal release speeds, launch angles, and hand positions. And yet, the best shooters don't calculate, they feel. They've trained their bodies to internalize math. Now let's zoom out to strategy. Sports like American football and baseball are filled with data. Coaches use probability models to decide whether to go for it on 4th down, or when to steal a base. In baseball, the rise of sabermetrics, a statistical approach to player evaluation, revolutionized the game. Batting averages gave way to on-base percentage. Fielding metrics replaced gut instinct. Lineups began to reflect math, not tradition. But this brings us to something deeper, the tension between numbers and narrative. Fans love drama, momentum, underdogs. But math is cold. It tells you what's most likely to happen, not what you hope will happen. This is why some resist the analytics revolution in sports. It feels like it removes the romance. But in truth, it reveals a different kind of beauty, the elegance of optimization, the symmetry of patterns, the way numbers describe human performance. Take soccer again. Each match is a swirling mix of chaos and control, but beneath that chaos, analysts now use spatial data and machine learning to track every pass, every run, every angle of attack. There's a metric called expected goals, XG. It calculates how likely a shot is to result in a goal based on location, angle, and context. It doesn't tell you what happened, it tells you what should have happened. Sometimes a team dominates the XG stats but still loses, because math measures probability, not fate. And what about tennis? Players don't just hit the ball hard, they aim for angles that are hardest to return, guided by geometry. Cross-court shots travel further, allowing more time. Down-the-line shots are riskier but rewarding. Elite players even vary shot placement to exploit psychological patterns. There's a kind of game theory in every rally, anticipating the opponent's expectations then doing the opposite. Math, here, becomes a kind of mind game. Let's pause for a moment and consider this. If math is everywhere in sports, why don't we notice? Because it's hidden beneath emotion. We cheer for goals, not equations, but without math, the magic wouldn't work. It's in the flight of a javelin, in the perfect dive of a gymnast, in the banking curve of a Formula One car taking a turn at 200 miles per hour, balancing centripetal force, tire friction, and downforce with exquisite precision. Even the human body is a biomechanical equation. Muscles convert energy into torque. Tendons store elastic potential. Runners optimize stride frequency and ground contact time, not consciously, but through feedback loops refined by training. Performance becomes math in motion, but there's something more beautiful still. In sports, math meets meaning. A game-winning shot isn't just an angle and velocity, it's legacy, memory, emotion. We remember the miracle moments not just for their precision, but because they felt improbable, and that's the paradox. The more you understand the numbers behind sports, the more you appreciate the awe of those moments when athletes defy the odds, when they do something statistically unlikely, yet unforgettable. So as you drift towards sleep, remember this: behind the roar of the crowd is a quiet rhythm of reason. Behind the instinct of a player is a lifetime of learned equations, and behind every game is the whisper of mathematics, invisible, elegant, and absolutely essential. Picture a quiet field just before sunrise. The sky is lavender, the grass still kissed with dew. Somewhere nearby, a beehive hums gently, a steady vibration of purpose, of instinct, of ancient design. Inside, thousands of bees move in concert, weaving around one another in impossible synchrony. But if you peer closer, much closer, you'll notice something astonishing. Their home is made entirely of hexagons, perfect ones, repeating endlessly. But why? Why hexagons? Why not circles, or triangles, or squares? The answer, as you're about to see, reveals something quietly breathtaking. A connection between biology, mathematics, and efficiency so profound, it borders on the philosophical. Let's begin with the comb itself. Bees build honeycomb as a storage system, for honey, for larvae, for pollen. These combs are made from beeswax, which is energetically expensive to produce. Every drop counts. So evolution, ever the silent engineer, drove bees to build with the least waste possible. This is where geometry comes in. The question: how do you divide a flat surface into equal areas, with no gaps, no overlaps, and the smallest possible perimeter? It turns out, of all the possible shapes, triangles, squares, octagons, only 3 can tile a plane without leaving any space. Equilateral triangles, squares, and hexagons. So which is best? Triangles have more edges, so more wall material is required. Squares are better, but hexagons hit a sweet spot. They cover space evenly. They use the least wax for the most storage, and they allow the maximum volume with minimum surface area. In 1999, a mathematician named Thomas Hales formally proved what bees had known for millions of years, that the hexagon is the most efficient shape for tiling a surface. It's called the honeycomb conjecture, and it took over 2,000 years to prove. Even the ancient Greeks suspected it. The Roman scholar Pappus of Alexandria wrote that bees possess a certain geometric forethought, as if nature had whispered mathematics to them in their sleep. But here's what makes this even more extraordinary. Bees don't understand geometry, they don't run calculations, they don't decide on hexagons, they just build driven by instinct. So how do they do it? When bees secrete wax and begin constructing the comb, they start with cylindrical tubes. As the wax warms either from ambient temperature or from the heat of the bees themselves, the wax softens slightly, surface tension, and the pressure from neighboring cells causes the wax to settle naturally into hexagonal forms. Like bubbles merging on a flat surface, they find the most efficient way to share space. What's remarkable is that this behavior, physical, chemical, collective, produces what appears to be an act of mathematical genius. It's a kind of emergent intelligence, a system where simple actions and constraints give rise to complex, optimal structures, and that raises a deeper question: where does intelligence end, and nature begin? If a bee, without conscious thought, can produce geometric perfection, if instinct can mirror the conclusions of centuries of human mathematics, then what, exactly, is intelligence? Maybe we're surrounded by quiet brilliance we don't recognize, not in algorithms or textbooks, but in the silent choices of evolution, the slow, graceful bending of biology toward what works best. Hexagons don't just live in honeycombs, you'll find them in basalt columns in Iceland, formed by the slow cooling and cracking of lava, in the compound eyes of insects, in turtle shells, in the polar vortex on Saturn's North Pole, a massive atmospheric hexagon thousands of kilometers across. It seems hexagons are nature's preferred compromise between strength, efficiency and symmetry. Even in man-made technology, hexagons show up. Think of carbon nanotubes, molecular structures, and even the pixel patterns in certain telescopes and camera sensors. These are engineered hexagons, mimicking what bees have always done. So the next time you see a honeycomb, remember this. It is a work of biological architecture and geometric precision, a solution to an ancient problem, discovered not through equations, but through trial, error, and necessity, repeated over millions of years. It is a shape born from simplicity, yet it reveals a kind of deep order in the universe. As you drift further into thought, reflect on this idea, that complexity doesn't always come from consciousness. Sometimes it comes from constraint, from repetition, from a quiet, unseen intelligence embedded in matter itself. And perhaps that's what math really is, not a human invention, but a language the universe already speaks, waiting for us to listen. From the honeycomb's quiet genius, we now turn to another form of silent complexity, a story where numbers carry secrets no one can break. Have you ever shuffled a deck of cards and wondered if what you just did was truly random? Maybe you rolled a die, flipped a coin, let a computer pick a number for you, believing, with quiet confidence, that the result was pure chance. But here's the unsettling truth. True randomness is far more elusive than we think. In fact, it may not even exist in the way we imagine. Let's begin with something simple: shuffling cards. There are 52 cards in a standard deck. When you shuffle them, you're arranging them into one of approximately 8 pick-and-half possible orders. That's an 8, followed by 67 zeros. So surely that's random, right? Well, not quite. Most human shuffles aren't random at all. Mathematicians have studied this. On average, it takes 7 proper riffle shuffles to randomize a deck. Anything less, and patterns remain. The way we cut, interlace and handle the cards often follows subtle habits, introducing structure into chaos. But that's just the beginning. What about flipping a coin? That ancient symbol of chance, heads or tails. In theory, a coin has a 50/50th chance of landing on either side. But in practice its path is governed by physics. The angle, the speed, the air resistance, the bounce, all calculable, all deterministic. In 2007, researchers at Stanford built a coin-flipping machine. Every toss was perfectly controlled. And guess what? The coin landed the same way almost every time. Turns out, if you knew all the forces at play, you could predict the outcome. The randomness vanishes under a microscope. It's not chance, it's complexity masquerading as chance. This brings us to a crucial distinction: pseudo-randomness versus true randomness. Most of what we call random, in computers, games or everyday life, is pseudo-random. That means it looks random, behaves randomly, but is generated by a deterministic process. Your computer doesn't just pick a number. It uses an algorithm, a formula that takes an initial value, called a seed, and produces a sequence of numbers that appears random. But if you know the algorithm, and the seed, you can reproduce the exact sequence. There is no mystery, just illusion. This is why cryptography, the science of secure communication, relies heavily on how hard it is to reverse these processes. We don't need real randomness, just randomness that's unpredictable to humans and machines. But then the question lingers: is true randomness even possible? To answer that, we turn to the quantum world, a place where uncertainty is woven into the fabric of reality itself. According to quantum mechanics, certain events, like the exact moment a radioactive atom decays, happen completely at random. No underlying cause, no hidden variable, just probability. You can't predict when the atom will decay. You can only say, there's a 50% chance it will decay within this time frame. This isn't due to ignorance. It's built into the physics. If quantum theory is right, and it continues to pass every experimental test, then the universe itself contains irreducible randomness. And yet, there are theories that challenge this. Hidden variable theories. Deterministic interpretations of quantum mechanics. Philosophers and physicists continue to debate whether randomness is real, or just a reflection of our limited perspective. Could it be that the universe is like a giant clock, intricate, precise, but ultimately knowable, and we just lack the tools to see its gears? Or is it more like a dream, fluid, probabilistic, guided by laws that only speak in likelihoods, not certainties? We don't know, and maybe we're not meant to. Even in nature, patterns emerge in what seems random: raindrops hitting a pond, leaves falling from trees, the chaos of a fire's flicker. All are governed by physical laws that make them appear unpredictable, but they're not truly random. They're just too complex to track. Randomness, then, becomes a kind of narrative trick, a story we tell ourselves when we can't see the full picture. It's comforting, in a way. It gives us space for luck, for freedom, for uncertainty. And yet, there's something haunting about the idea that nothing, not even the flip of a coin, is truly free from cause. If everything follows a chain of events, then maybe everything was always going to happen this way. Pause for a moment. Think about the last random thing that happened to you: a chance meeting, a sudden idea, a roll of the dice. Was it really random, or was it the inevitable consequence of 1,000 tiny details, converging quietly beneath your awareness? Either way, it humbles us. Because in our search for chaos, we often find structure, and in our search for order, we often find mystery. So the next time you shuffle cards, or pick a number, or gaze at the stars wondering why some things just happen, remember this: randomness might be real, or it might be the mask that complexity wears when it doesn't want to be understood. From the unpredictable, we shift now to the philosophical, a paradox that challenges the very logic we use to define certainty. You're walking through a casino. The sounds are hypnotic: the soft chime of slot machines, cards being shuffled, dice bouncing across felt. The lighting is dim but warm. Everything is engineered to feel inviting. Now take a deep breath. What you're entering isn't just a room of games. It's a carefully constructed mathematical machine, a system where every wheel, every deck, every roll has been tuned, with precision, to work against you. Casinos don't rely on luck. They rely on statistics. And that's where this story begins. Every game you see in a casino, whether it's blackjack, roulette, craps, or a flashing slot machine, is built around a core idea: expected value. Expected value, in simple terms, is what a player can expect to win or lose over time, on average. And here's the catch: in every game, the expected value for the player is negative. Not because of cheating, not because the games are rigged in the traditional sense, but because of math. Take roulette, for example. In European roulette, there are 37 numbers, 1 through 36, plus a single zero. If you bet on a single number, you'll be paid 35 to 1 if it hits. That sounds fair, but it's not. There are 37 possible outcomes, so your actual chance of winning is 1 in 37, but you're only being paid as if the odds were 1 in 36. That tiny gap, that statistical sliver, is where the house makes its money. Now consider American roulette, which adds a second zero, bringing the total to 38 numbers. Even worse odds, same payout, greater edge. This advantage is called the house edge, the mathematical cushion that guarantees the casino will make money over the long run. In roulette, that edge is around 5.26% on most bets. That means for every $100 wagered, the casino expects to keep about $5.26. But that's just one game. Let's walk to the slot machines, the glowing giants of the casino floor. Unlike table games, slots don't show you the odds. They run on random number generators, designed to produce results that are statistically random, but not uniform. Each machine is programmed with something called a payout percentage, often between 85% and 98%. That sounds generous, but remember, that's over tens of thousands of spins. It's not about whether you win tonight, it's about whether the system profits over time, and it always does. Because those percentages are chosen carefully, to offer enough small wins to keep you playing, but not enough to beat the math. This is known as intermittent reinforcement, a concept rooted in behavioral psychology. When rewards are unpredictable but frequent enough, they create a powerful feedback loop in the brain. Dopamine surges, time melts away, you lose track of how much you've spent, and the statistics keep grinding silently in the background. Even in games where player choices matter, like blackjack or poker, the math looms large. In blackjack, the house edge is relatively low, as little as 0.5%, but only if you play with perfect strategy. Most players don't. Casinos count on this. They know the average player will make mistakes, hitting when they shouldn't, standing when it's unwise, splitting pairs poorly. Each deviation tilts the odds in the house's favor. Even card counting, the legendary technique used to beat blackjack, isn't illegal, but casinos watch for it constantly because it threatens their statistical advantage. The moment that edge disappears, the system breaks. That's how tightly the whole structure depends on probability. It gets more intricate when you look at progressive jackpots, like those in slot machines or some table games. They offer massive prizes that grow over time, but the odds of winning are astronomical, often 1 in 10 million or worse. The jackpot serves as bait, statistically offset by thousands of tiny losses. The math is balanced, and the house always wins. But here's the unsettling truth. Many players believe they're beating the system. They remember their rare wins, forget their frequent losses. This is known as selective recall, and it's part of a larger set of mental biases, like the gambler's fallacy, where people believe a win is due after a string of losses. These aren't just quirks, they're predictable behaviors that casinos exploit. Psychology meets probability, emotion meets statistics, and the machine keeps spinning. Now, this doesn't mean people shouldn't gamble. There's nothing inherently wrong with playing a game of chance for entertainment, but understanding the math behind it changes the perspective. You realize you're not playing against other people, you're playing against statistical inevitability, a calm invisible force that doesn't cheat, it just waits. So next time you walk through a casino, or open an online gambling app, pause, feel the smooth surface of the dice, the hum of the slot machine, the rhythm of the roulette wheel. Each one is a quiet algorithm, turning, calculating, extracting. It's not malicious, it's just math. And math, as we've seen again and again, is indifferent. From games of chance, we'll now return to games of logic. Paradoxes that twist not your wallet, but your mind. Picture your thoughts, not as words or voices, but as patterns. Waves. Connections flickering across a web you cannot see. Now consider this, your mind. This swirling constellation of memory, sensation, and self may run on a kind of mathematics. Not numbers you consciously work with, but deep, instinctive patterns, shapes of logic, that guide every choice you make, and most of them, you never notice. The brain is often compared to a computer. It's not a perfect analogy, but in some ways, it fits. Input comes in through your senses, is processed internally, and then becomes thoughts, reactions, emotions, even dreams. But unlike a machine that runs on explicit code, the human mind works through neural networks, vast systems of interconnected cells, each firing or staying silent in response to the ones around it. These networks create patterns, sequences, and structures that form everything you experience. And here's where the mathematics begins. Your brain doesn't store images like a camera, or language like a book. It builds abstractions, simplified, mathematical models of the world. When you see a face, you're not memorizing every pore or wrinkle. Your mind distills the shape, the geometry of eyes, the symmetry of the mouth, the angles and ratios. Even infants respond more to faces with average symmetry, a subconscious calculus already at work. This isn't shallow, it's efficient, it's how we survive. From recognizing danger in a pattern of shadows, to intuitively understanding the rhythm of speech, the brain is constantly solving problems. It finds order in chaos, structure in noise. Every time you speak, your brain chooses from among thousands of words, in real time, calculating what fits, syntactically, semantically, emotionally. It feels automatic, but underneath is a fluid algorithm, a math of meaning. Even emotions follow patterns. The sudden spike of fear, the slow build of anticipation, the up-down curves of laughter. Our minds move like functions, responding to stimuli, plotting reactions along invisible axes. And just like mathematical systems, they can loop. Anxious thoughts often form feedback cycles, patterns that reinforce themselves. The more you worry, the more your mind searches for proof that there's something to fear. This is a recursive loop, like a function calling itself, over and over. Understanding this gives us a strange power, the ability to step back and see our thoughts, not just feel them, to notice the equation running in the background, and maybe change it. This is the basis of many therapeutic models, like cognitive behavioral therapy, where the goal is to rewire those thought loops, to replace dysfunctional patterns with healthier ones. It's like debugging the code of the mind. But perhaps even more mysterious is how these patterns emerge in the first place. When you learn something new, a word, a dance, a face, your brain changes physically. Connections are rewired, pathways restructured. This is called neuroplasticity, and it's one of the most mathematically elegant features of the brain. It learns by trial and error, like a neural network in artificial intelligence. It strengthens the connections that lead to success, and weakens the ones that don't. Over time, You build a model of the world, not a perfect replica, but a compressed intuitive simulation, full of predictions, shortcuts, biases. You don't see the world as it is, you see it as your mind has modeled it. This explains strange phenomena, like optical illusions, déjà vu, or false memories. The brain fills in gaps based on pattern recognition. It extrapolates reality, and sometimes, it guesses wrong. Still, this doesn't mean we're broken. It means we're adaptive. Math isn't just numbers, it's the science of patterns, and your consciousness may be its most complex expression. Take a breath. This idea, that you are a pattern, can feel unsettling, like you're a machine of probabilities, a logic system made of flesh. But it can also be beautiful, because patterns evolve, they bend, they grow, and no two minds, no two equations are ever quite the same. You are a singular waveform, an algorithm no one else has ever run, and never will again. Even now, as you listen, your brain is mapping rhythms, forming expectations, softening your thoughts into the shape of sleep. It's mathematics, humming quietly beneath awareness, shaping who you are. Imagine a cube. Sharp edges. 6 square faces. You can picture it clearly. Now imagine unfolding that cube into 2 dimensions. What do you get? A cross-shaped pattern. 6 squares arranged to be folded back into form. Simple, right? Now, try the same with a 4-dimensional cube. It's called a tesseract, the 4D analog of a cube. But unlike the familiar cube, the tesseract can't be seen in full, not by us, not in this dimension. We can draw projections, shadows, wireframes that twist and rotate in ways that feel wrong, surreal, as if they're breaking the rules of geometry. And in a way, they are, because the tesseract lives in 4 dimensions of space, not time, actual spatial direction beyond the 3 we know, left, right, up, down, forward, backward. But what could a 4th spatial direction possibly mean? Take a moment. In 2D space, a flat world, you can move in 2 directions. Creatures in that world would have no concept of up, it wouldn't exist for them. Now imagine us 3D beings. We move freely through space, unaware of what lies beyond, in the direction we simply can't move. That's what 4D space is to us, not an imaginary fantasy, but a legitimate mathematical extension, just like 3D is to 2D. And here's the strange part. The math works. We can define shapes, rotations, volumes. The tesseract has 16 corners, 32 edges, 24 square faces, and 8 cubic cells. Every part is logically consistent. We can even rotate it, mathematically, through 4D space. But our minds can't visualize it. Not completely, only shadows. This is one of the quiet, humbling truths of higher mathematics. It reaches past what we can see or imagine, into forms that challenge our intuition at every step. And it doesn't stop at 4 dimensions. Mathematicians regularly work with 5D, 6D, 26D, even infinite dimensional spaces, not as thought experiments, but as tools, real rigorous structures used in physics, computer science and beyond. In string theory, for example, the fundamental particles of the universe are tiny vibrating strings existing in 10 or 11 dimensions, most of them compactified, curled up so tightly we can't detect them. These extra dimensions aren't just abstract, they're necessary for the math to make sense, for the theory to be consistent. Let that settle in. The reality we move through might be a shadow of something much larger, much more intricate, a hyperdimensional landscape, where what we perceive as particles are just intersections of higher dimensional objects. It's almost spiritual, and yet, the logic is grounded, the math holds. This brings us to the idea of impossible shapes, like the Penrose triangle, or the Escher staircase. These are optical illusions, but they hint at something deeper, our brain's limitation in grasping certain forms. In higher dimensions, impossible shapes become possible. The rules change. The triangle that loops back on itself without end, that might be a projection of a higher dimensional object into 2D space, distorted the way a shadow warps a hand into an unrecognizable blur. In 3D, a Mobius strip, a surface with only one side, is already strange. But in 4D, we can create objects with no distinct inside or outside, surfaces that loop through themselves, seamlessly, with no beginning or end. These aren't magic tricks, they're mathematical truths. It's easy to forget how powerful abstraction can be, how math, unlike the senses, is not limited by the dimensions we inhabit, it moves beyond them, freely, and in doing so, it gives us glimpses, brief, awe-filled moments, of a reality much richer than what our eyes can see. So next time you look at a cube, remember, it's just one step up a ladder of complexity that stretches toward infinity. A single rung in a structure that defies space itself. Let that be a comfort. A reminder that the universe is deeper than it appears. And maybe, so are you. Because if reality hides dimensions we can't see, who's to say the self doesn't as well? You flip a coin into the air. Heads or tails. You don't know until it lands. But you believe, deeply, that it was always one or the other. That even in the air, it had a hidden answer, waiting to be revealed. Now imagine a different kind of coin. One that doesn't choose until you look. A coin that exists in a hazy, shimmering state. Not heads, not tails, but both at once. And the moment you observe it, it chooses. As if your attention collapses its possibilities into a single outcome. This is not science fiction. This is the strange, unsettling truth of quantum mechanics. The mathematical framework that describes the behavior of the tiniest particles in the universe. At the heart of it lies something deeply unintuitive. Superposition. The idea that a particle, like an electron or a photon, can exist in multiple states simultaneously. Not metaphorically. Literally. Let's go deeper. In the classical world, things have definite properties. A light switch is on or off. A cat is alive or dead. A particle is here or there. That's how reality behaves on the surface. The world of trees, chairs, clouds. But at the quantum level, certainty breaks down. Particles don't exist as solid dots. They exist as probability waves. Fields of potentiality, smeared across space. Until measured, they are not anywhere in particular. They are everywhere they could be. This was first captured in the famous double-slit experiment, when particles like electrons are fired one at a time through two slits onto a screen. They form a pattern not of particles, but of interference, like waves colliding, as if each particle goes through both slits at once, interfering with itself. The mode. And here's the eerie part. The moment you observe which slit it goes through, the interference pattern vanishes. The particle picks a path. Reality collapses into a single version. It's as if the universe waits to decide, until you look. This has led to a cascade of interpretations and philosophical debate. Does observation cause reality to crystallize? Is consciousness required for collapse, or is measurement just interaction? One particle nudging another, forcing a choice. No one knows for sure. But the math is clear, and it works, stunningly well. Quantum mechanics is the most accurate predictive model in all of science. It gave us lasers, semiconductors, transistors, GPS, quantum computing. It is woven into the fabric of modern life, and yet it refuses to be understood intuitively. It's like the universe speaks a different language in its smallest whispers, and when we listen, we find logic breaking apart, not in chaos, but in possibility. Take entanglement, a quantum phenomenon, where two particles become linked, so that the state of one instantly determines the state of the other, no matter how far apart they are. Change one here, and the other responds, even if it's on the other side of the galaxy. Einstein called this spooky action at a distance. He resisted it, couldn't accept it, but experiment after experiment confirmed it. Information seems to travel faster than light, or perhaps doesn't travel at all, as if distance doesn't apply in the same way at this scale. Pause here. This isn't just about particles, this is about what reality is. Is the universe made of solid things, or of relationships, of probabilities, of hidden dimensions we cannot see? Quantum theory suggests that the world is not a thing, but a wave of unfolding potential, gently collapsing into form, and we are not separate observers, we are participants. When you listen, when you watch, when you measure, you're not just gathering information, you are changing the outcome. The quantum coin lands on heads or tails, because you chose to flip it. Let that idea settle in. That consciousness, or at least interaction, is entangled with reality itself. That observation is not passive, it's creative. You are not watching the movie of the universe, you are helping to write it. And so the smallest things, electrons, quarks, photons, teach us the largest truths. That certainty is an illusion, that the world is stranger than it seems, that mathematics doesn't describe what is, it describes what can be. Quantum theory, with all its uncertainty and elegance, reminds us that the universe is not made of things, but of potential, coalescing moment to moment. So as you let your mind drift, imagine yourself as part of that wave, a fluctuation in the great field of possibility, a gentle ripple in the ocean of being, neither fully here nor there, but momentarily, beautifully, both. And now, from the shimmering edge of quantum mystery, we return to something more grounded, but no less strange. Imagine a library. Not just any library. A vast, infinite one. Every shelf filled with books containing truths. Every law of math, every logical theorem, every proof that could ever be written. Now imagine a strange discovery. Within this infinite library, there are some truths that can never be found on the shelves. Not because they don't exist, but because the system itself can't contain them. This is the unsettling reality introduced by Kurt Gödel, a quiet, brilliant logician from early 20th century Vienna. He proved something that shook the foundations of mathematics and logic forever. It's called Gödel's incompleteness theorems. And what it tells us is this. In any system of logic rich enough to contain arithmetic, no matter how carefully you build it, no matter how perfect the rules, there will always be statements that are true but can't be proven within the system. Take a moment with that. Some truths will always lie just out of reach, like stars you can see, but never touch. Let's unfold the story gently. At the time, many mathematicians, including the famed David Hilbert, believed that mathematics could be made complete and consistent, that we could find a finite set of rules that would capture every truth. No ambiguity, no paradox, just pure mechanical certainty. Hilbert's motto was "We must know, we will know." And then came Gödel. In 1931, at just 25 years old, he published a paper that quietly unraveled the dream. With razor-sharp precision, he showed that any logical system capable of doing basic arithmetic will either be incomplete, meaning some truths can't be proven, or inconsistent, meaning contradictions can be derived. You can't have both completeness and consistency. One must give. How did he do it? Gödel built a bridge between numbers and logic. He assigned numbers to every symbol, every rule, every step in a proof. This process, called Gödel numbering, turned logic itself into arithmetic. Then, using these numbers, he crafted a self-referential statement, a sentence that, in essence says, this statement cannot be proven. If the system could prove the statement, it would be wrong, because the statement says it's unprovable. But if the system can't prove it, then it's true, and yet unprovable. This isn't just wordplay, it's airtight, formal, inevitable. Gödel had found a truth the system couldn't reach. It's like a mirror reflecting itself into infinity. A loop that logic alone can't break. Take a breath here. This result is deeply humbling. It tells us there are limits to formal reasoning. No matter how complete our system, how advanced our technology, how clever our minds, some truths will always remain outside the frame. It's like trying to define the edge of a map from within the map itself. You can get close, you can approximate, but you'll never quite escape the borders. And this has enormous implications. In mathematics, it means no system can prove its own consistency. We can't build a perfect foundation. There will always be cracks, or at least, hidden doors we can't open from the inside. In computer science, it connects to the halting problem, the question of whether we can know, in advance, whether a program will finish running, or loop forever. Alan Turing, inspired by Gödel, proved that we can't always know. Some problems are fundamentally undecidable. Even in philosophy, the echoes of Gödel's theorems linger. They challenge the idea of absolute knowledge. They suggest there will always be mysteries, not because we're not smart enough, but because reality is inexhaustible. Every system has blind spots, every mind has limits, and perhaps that's a kind of grace. Because if everything could be known, predicted, proven, where would the wonder go? Gödel's theorems leave room for mystery, for creativity, for the thrill of chasing something that can never be fully caught. And it makes you wonder, what truths lie beyond logic? What parts of reality, or of ourselves, can never be captured in equations or proofs? Maybe the things that matter most, love, beauty, meaning, live in that unreachable space. So tonight, as you drift gently towards sleep, let this truth settle into your thoughts. Not everything has to be solvable. Some truths are better felt than proven. Some paradoxes are part of the design. Let that be comforting, a soft edge to the mind's desire for certainty. Imagine nothing. Not an empty room. Not darkness. Not air. Just the absence of anything. A blank. Now imagine trying to count that. What number do you assign to the void? To absence itself? For most of human history, the answer was, you don't. The concept of zero, the symbol we now casually write every day, is one of the most recent, most revolutionary ideas in all of mathematics. And once upon a time, it didn't exist. In fact, for thousands of years, zero was feared, avoided, considered dangerous. Because it represented more than just a placeholder. It represented nothingness, the great silence at the heart of being. And for many ancient thinkers, that was too terrifying to name. The earliest number systems, in ancient Egypt, Babylon, Greece, had no symbol for zero. You could write 10 or 100, but not none. Even the great philosopher, Aristotle, rejected the idea of a void. In his worldview, nature abhorred a vacuum, but something changed in the East. Around the 5th century CE, Indian mathematicians began to formalize the concept of shunya, a Sanskrit word, meaning emptiness or void. They used a small dot to represent it, not as a mistake or absence, but as a number in its own right, one that could be added, subtracted, multiplied. This was a radical shift, because zero isn't just the absence of quantity, it's the presence of nothing, a paradox if ever there was one. It's a value that holds space, that gives structure. Without it, place value systems don't work. Try writing 101 without a zero. You can't. It becomes 11 or 1001. Ambiguity reigns. By the 9th century, the concept of zero traveled west, carried by Islamic scholars like al-Khwarizmi, who would give us the word algebra. In his works, he used the concept of zero, not just as a placeholder, but as a foundation for solving equations. And as it spread into Europe, resistance returned. Even in medieval times, many viewed zero with suspicion. It didn't behave like other numbers. You couldn't divide by it. It introduced the idea of infinity, the ultimate unknown. To divide by zero is to break the rules, to fall into the abyss. And yet, we could not live without it. Zero gives balance. It defines neutrality, equilibrium, the center between opposites. In temperature, it's the point where freezing begins. In electricity, it's ground. In philosophy, it's non-being, the starting point of existence. And in mathematics, it's the seed of modern computation. Without zero, binary code, the language of computers, wouldn't exist. Every program you've ever used, every bit of data, is built from 1s and 0s, presence and absence, on and off, light and shadow. Take a breath here. Isn't it strange that the very machine you're listening to this on, the device that streams this calm, quiet voice, runs on nothing, or rather, runs on the idea of nothing? Zero is more than a number. It's a conceptual gateway. It bridges math and metaphysics. It poses deep questions. If zero exists, what is it? Is it something, or is it nothing? Can you measure the absence of measurement? This is what makes zero so powerful. It's not just a hole, it's a mirror, a blank, that lets us reflect, a starting point, a reset. And it behaves oddly. Zero multiplied by anything is zero. It absorbs. It wipes out. Zero added to anything changes nothing. It disappears. And yet, raised to the power of anything, it still vanishes. It's like a mathematical ghost, present, but elusive. In algebra, zero is the solution to countless equations. In calculus, it defines the derivative, the limit, the precise turning point of change. It's the heart of the origin in geometry, the zero, that everything radiates from. Zero gives us symmetry, balance, space. And in physics, it leads us to the mysteries of the quantum vacuum, a state with no particles, no fields, and yet teeming with energy. Because even nothing isn't really nothing. The void, at the smallest scales, bubbles with uncertainty, flickers of possibility, borrowed energy, that appears and disappears in a blink. So zero isn't just the beginning of math, it's the beginning of everything. Without it, there is no counting, no equations, no digital world, and perhaps, no way to even conceive of what isn't. It's fitting then, that this symbol, a circle, an empty loop, looks like the cycle of life itself. It begins nowhere, ends nowhere, always returning, always present. Let this sink in. What we call nothing, may be the most important something of all. As we leave behind the empty serenity of zero, our next step takes us into structure, into rules, into invisible languages that guide everything we do, from logic to ethics, from puzzles to paradoxes. Try to imagine a line that never ends, a road with no final turn, a staircase that climbs forever. Now, try to imagine something even stranger, not just endlessness, but sizes of endlessness, different kinds of infinity. The human mind resists this. We're built to count, to measure, to compare. A cup of water, a day's length, a galaxy's width, but infinity slips through our fingers like fog. It has no boundaries, no edge, and yet, somehow, we've captured it in mathematics. And what we found there was even more mind-bending than we expected. Infinity is not a number, it's a concept, an idea, a representation of something unbounded. But math treats it with care, like a wild animal, not quite tame, not fully trusted. Why do you first encounter infinity? In simple counting, you can count forever. Add one, then another, and another. The set of all natural numbers, 1, 2, 3, 4, never ends. This is called a countable infinity, and already it challenges us. If it never ends, how can it be a set? How can we compare it to anything? But things get even stranger when we look between the numbers. Between 1 and 2, there are an infinite number of fractions, 1.1, 1.01, 1.001, and so on. But also irrational numbers like the square root of 2, or pi. The number of these in-between values is uncountably infinite. It's a bigger infinity, a larger kind of endless. This was discovered by George Cantor, a mathematician, who quite literally lost his mind exploring infinity. He showed that there are multiple sizes of infinity, a discovery so radical, it was rejected by many of his peers. But the math held. Cantor proved that the infinity of real numbers, all the decimals, is larger than the infinity of whole numbers, and that you can keep going, creating a hierarchy of infinities, each one larger than the last. Infinity has structure, levels, depth. Pause and breathe for a moment. Let this idea settle that something can go on forever, and yet something else can go on even more forever. It's not just abstract. Infinity appears in physics too. In cosmology, some theories suggest the universe might be infinite, in space or in time, or both. If the cosmos has no edge, then somewhere out there, in the distant stretch of space, there might be a copy of you, thinking this same thought. In quantum mechanics, infinite possibilities hover in superposition, collapsing into reality when observed. In calculus, we use limits and infinite series to describe smooth motion, area under curves, or the sum of infinite steps that somehow converge to a finite answer. Zeno's paradox asked, if you keep cutting the distance in half, how do you ever get anywhere? And calculus answered, through infinity. We even have shapes with infinite detail. Fractals again, where zooming in reveals more structure. Forever. Nature seems to flirt with infinity at every turn. Snowflakes, coastlines, branching trees, finite in size, infinite in complexity. And yet, there's a warning here. Infinity can break the rules. In physics, certain equations lead to infinite results, a sign that the model has collapsed. In black holes, matter compresses into a singularity, a point of infinite density. Time and space dissolve. Our math no longer works. Infinities are both guides and boundaries. They show us where understanding fails, where we've reached the edge of what can be known, and they invite us to keep going, because infinity is not just size, it's also possibility, the infinite complexity of the human brain, the infinite potential combinations of thoughts, dreams and questions, the idea that no matter how much we know, there will always be more to wonder. You might think that contemplating infinity would be terrifying, but there's something oddly peaceful in it, a kind of surrender. You don't have to reach the end. There isn't one. You are part of a continuum, a thread in an unending weave, and that's okay. So let yourself dissolve a little now. Let your thoughts stretch out like stars in the night sky, growing dimmer, more distant, as they approach the horizon of the infinite. Let yourself be part of that impossible size, not apart from it, of it. And as we drift out of infinity, we find something else waiting, something hidden in plain sight, because the numbers we use every day, whole, friendly, familiar, are not as solid as they seem. Behind them lies an ancient riddle, a hidden flaw, a strange idea that one might not equal one, in certain infinite conditions. Try to picture time. Not a clock, not a calendar, not the ticking or the pages turning, but time itself. What does it look like? For most of us, time feels like a river, flowing forward, pulling us along with it. The past behind us, the future ahead, and the present, slipping by, second by second. But what if that's not what time is at all? What if time isn't flowing, but fixed? And what if the passage of time, the feeling of now, is just an illusion? These are not just questions for poets or philosophers. They are rooted in physics, in math, in the very structure of the universe. Let's start with a familiar idea. Time is the fourth dimension. In everyday life, we experience three dimensions of space: up, down, left, right, forward, backward. Time adds the fourth. It tells us when something happens. Where space describes location, time describes change. But in Einstein's theory of relativity, space and time aren't separate things. They are woven together into a single fabric space-time. In this model, the universe is not a stage on which events happen. It is the stage, and the events are part of its shape. Movement through space affects how time is experienced, and vice versa. If you move very fast, near the speed of light, time slows down for you. This isn't theory, it's measured, confirmed. Astronauts aboard satellites age slightly slower than people on Earth, not because time is broken, but because it's relative, and gravity also bends time. The closer you are to a massive object, like a planet or black hole, the slower time flows for you, compared to someone farther away. This is known as gravitational time dilation, and it's not science fiction, it's essential for your GPS to function. Without adjusting for it, satellites would drift wildly out of sync with Earth time in just a few hours. So, what does this mean? It means that time is not universal. There is no single ticking clock for the cosmos. Each observer carries their own time, their own now, but it gets stranger. Some physicists believe that all moments in time, past, present and future, already exist, just like all points in space. In this view, known as the block universe theory, time doesn't pass. Instead, the universe is a four-dimensional block, a vast frozen structure where every moment is etched, forever. Your birth, this very breath, your last heartbeat, all coexisting as part of a grand unchanging architecture. You are not moving through time, you are extended through it. It's a radical idea, one that defies our intuition. Because we feel time moving, we remember the past, not the future. We age, we change, we experience causality. But perhaps those feelings are not evidence of time's flow, but of how consciousness processes events, like a flashlight, moving through a photo album, illuminating one frame at a time. The album isn't moving, we are. Pause here, reflect. What if every moment you've ever lived still exists, somewhere, in the geometry of space-time? What if your entire life is not a line you walk, but a shape you are? And yet, from this cold, crystalline structure comes something deeply personal, the sense of now. No one knows exactly what now is. Some say it doesn't exist in physics, it's a human invention. Others argue that quantum mechanics, with its probabilistic nature, might inject real indeterminacy into time, that the future isn't fixed, that becoming is real. But the math remains stubbornly elegant. The equations that govern motion, whether Newton's, Einstein's, or quantum field theory, do not prefer a direction. Time could go forward or backward, and the math would still work. This symmetry suggests that time's arrow, from past to future, is not baked into physics, but arises from entropy. Entropy is the tendency of systems to move from order to disorder. Ice melts, buildings crumble, you age, not in reverse. But this arrow is not fundamental. It's statistical, it's likely, not certain, and at the smallest scales, the quantum level, even this breaks down. Particles can move backward in time. Virtual particles flicker in and out of existence, unbound by classical cause and effect. Time, it seems, is not as solid as we thought. So where does this leave us? In a universe where time is bendable, relative, possibly illusory, where the past and future might coexist, where the present is not a point, but a perspective. And in that perspective, you are here, listening, breathing, thinking, a brief consciousness floating through a dimension you can't see, measuring change with each heartbeat. Maybe you've felt it before, in dreams, in déjà vu, in those quiet moments where time seems to stop. Perhaps what you're feeling isn't time slowing, but your awareness slipping sideways, catching a glimpse of the fourth dimension. So let it slow now. Let your mind drift unhooked from minutes and hours. Let yourself be a part of something wider, something timeless. Far above you, in the dark stillness beyond clouds and weather, planets drift. They move in silence, spiraling around the sun, pulled not by strings, but by something invisible, something ancient, something precise. We call it gravity, but gravity isn't just a force, it's a sculptor, shaping the motion of moons, planets, comets and stars into elegant mathematical dances. It creates orbits, predictable, beautiful curves that hold the solar system in balance, and the math that describes it. It's astonishingly simple and endlessly profound. It all begins with Isaac Newton. In the 17th century, he watched an apple fall, or so the story goes, and asked a question that changed everything. If the apple falls, does the moon fall too? From that question came the law of universal gravitation. Every mass attracts every other mass, with a force proportional to their masses, and inversely proportional to the square of the distance between them. A simple equation. But from it, you can calculate orbits, planetary paths, even the trajectories of spacecraft and satellites. Think about that. From your backyard, you can write a formula that explains the movement of Jupiter, Saturn, or distant asteroids. The universe isn't chaotic, it's clockwork, and gravity is its timekeeper. But here's the twist. Gravity doesn't just pull, it bends. According to Albert Einstein, gravity isn't even a force at all, it's the curvature of space-time. Massive objects like stars and planets warp the very fabric of the universe around them. Imagine laying a bowling ball on a rubber sheet. A marble placed nearby will roll toward it, not because it's pulled, but because the surface itself is curved. This is how orbits work. The Earth isn't being pulled in a circle, it's following a straight path through curved space. A geodesic, the shortest path in a distorted reality. And this distortion follows math. Every planet's orbit can be described using ellipses, as first discovered by Johannes Kepler. He noticed that planets don't move in perfect circles, but in stretched ovals, moving faster when they're close to the sun, and slower when far away. Kepler didn't know why, but Newton's math explained it, and Einstein refined it. This precise, predictable behavior is what allows us to send satellites into orbit, or land rovers on Mars. It's why tides rise and fall, why we have seasons, why eclipses can be predicted down to the minute, decades in advance. Take a moment to consider that. We live on a rock hurtling through space at 67,000 miles per hour, orbiting a star, along with other planets, each tracing a path governed by equations, and we don't fall off. We don't crash into the sun, we stay balanced because of math. It's a kind of cosmic choreography, a dance without music, only motion, gravity, and geometry. But orbits can become unstable too. In chaotic systems, like three or more bodies moving under mutual gravity, the math becomes unpredictable. Tiny changes in starting conditions can lead to wild, divergent outcomes. This is the three-body problem, and it haunted physicists for centuries. Even today, it resists simple solutions. It reminds us that beneath the precision, there is a shadow of uncertainty, a whisper that even in gravity's perfect clockwork, some gears spin strangely. Still, most orbits hold. Moons orbit planets, planets orbit stars, stars orbit the center of galaxies, and galaxies themselves orbit in vast clusters, drawn together by dark matter and invisible gravity. We still don't fully understand, and we are part of this motion. Right now you're not just sitting or lying still, you are spinning with the Earth, orbiting the Sun, moving with the galaxy, all of it governed by silent, invisible mathematics. There's something deeply humbling in that. To realize that you are part of a structure so immense, so precise, that your entire life unfolds within its turning gears, that the sunrise, the moonlight, the seasons, all are products of orbital math. But maybe there's also comfort, because if gravity is a sculptor, it doesn't just pull, it holds, it keeps the planets from drifting off into the void, it keeps the Earth at just the right distance from the sun, it allows time to unfold, steadily, in a spiral of motion. And that spiral leads somewhere. Picture a tree, not just the trunk or the leaves, but the shape of it, the way the branches split, and those branches split again, smaller and smaller, reaching outward like fingers tracing the edges of the sky. Now zoom in. Look at just one branch. Notice something strange. It looks like the whole tree. This pattern of self-similarity, of infinite repetition within finite space, is the language of fractals. Fractals are more than shapes. They are a mathematical revelation, a way of seeing the world that unveils order in places once dismissed as chaotic. Coastlines, lightning bolts, blood vessels, clouds, mountains, all of them seem wild, irregular, until you look closer and realize they're all speaking the same geometry. The term fractal was coined by mathematician Benoit Mandelbrot in the late 20th century. He noticed something odd while studying natural forms. Unlike the perfect lines and curves of traditional geometry, circles, squares, triangles, the real world is jagged, fragmented, rough, and yet not random. There was structure in the chaos. He discovered that many of these irregular shapes could be described using a recursive process, equations that feed into themselves. Repeat the process again and again, and a complex, infinitely detailed pattern begins to emerge. Take the Mandelbrot set, one of the most famous fractals. It's created by applying a simple formula, z equals sine z quadrado plus c, where z and c are complex numbers. That's it. But when you iterate this equation thousands, millions, billions of times, the image that forms is indescribably intricate. Zoom in forever, and you'll keep finding detail. Spirals within spirals, patterns repeating at smaller and smaller scales. It's like math has created its own universe. Fractals are infinitely complex, yet bound within a finite space. You can draw them on a screen, print them on a page, and still you'll never reach the bottom of their depth. This isn't just mathematical art, it's a blueprint of the world. Look again at that tree. Its branching follows a fractal pattern. So do rivers, splitting into tributaries. So does your circulatory system, your lungs, even the neurons in your brain. These systems need to distribute blood, air, energy across a wide area. Fractal design is efficient. It allows the greatest reach with the least energy. Fractals are nature's way of optimizing complexity, and this self-similarity across scales is a kind of natural poetry. It blurs the line between micro and macro, the tiny and the vast. When you look at a satellite image of a mountain range, and then at the chipped edge of a rock, they mirror each other. It makes you wonder, is the universe itself built from repetition? Do the rules that govern galaxies echo the ones inside atoms? Take a moment to let that idea sink in, that the shape of a cloud may have more in common with the pattern of a cauliflower than we ever imagined. That what looks random may simply be complexity too deep for the eye to catch without slowing down. Fractals also have emotional implications. They challenge our perception of perfection. In traditional geometry, beauty was symmetry. In fractal geometry, beauty is roughness, imperfect repetition, the texture of the real. It invites us to embrace complexity, not fear it. To understand that systems can be unpredictable in detail, but still predictable in shape, and that's powerful. In financial markets, fractals help model volatility. In medicine, they help analyze heart rhythms. In computer graphics, they generate lifelike landscapes, textures and clouds. Fractals give us a framework to simulate reality, not with straight lines, but with layered chaos. But they also carry a spiritual undertone, because when you stare into a fractal, like the Mandelbrot set, you feel something shift, something almost unsettling, like you're glimpsing a truth too vast to fully grasp. An infinite hallway of mirrors made from math, a portrait of order, born from the repetition of simplicity. What does it mean that such beauty comes from a simple equation, that infinite complexity is hidden in a formula, barely a line long? It suggests that the universe may not be complex because it's chaotic, but because it's deeply recursively simple, and perhaps we are too. When you dream, when you think, when you breathe, your patterns ripple outward, branching and curling like fractals. You are not a machine, you are a living equation, a process repeating in time, and as your mind drifts into rest, you may feel that soft spiral beneath your thoughts, tactile rhythm of breath, the recursive flicker of dreams. So tonight as you close your eyes, know this: you are made of patterns too vast to fully know. Your thoughts echo ancient geometry, your life branches outward, endlessly, like the shape of trees, or lightning, or galaxies. There's a rhythm in nature that you've seen 1,000 times, whether or not you noticed. It's in the curl of a fern, the twist of a pine cone, the seeds in a sunflower. It's in the horns of a ram, the spiral of a snail's shell, the arms of galaxies light years away. A secret pattern, recurring again and again, hiding in plain sight. It's called the Fibonacci sequence. It begins simply 0, 1, 1, 2, 3, 5, 8, 13, 21, and on it goes. Each number is the sum of the two before it. The math is simple, almost childlike, but the consequences are astonishing. The Fibonacci sequence isn't just a list of numbers, it's a blueprint, one that nature seems to follow when it grows. Take a sunflower. Its seeds are packed in a spiral pattern that seems almost chaotic at first glance, but count the spirals moving clockwise and counterclockwise, and you'll likely find two Fibonacci numbers, 34 and 55, or 55 and 89. Always two consecutive values, always part of the sequence. Why? Because this arrangement is mathematically efficient. The Fibonacci spiral, a logarithmic spiral built from the sequence, allows seeds to be packed tightly without overlap. It's the most optimal use of space and light. Nature, it seems, chooses math not for beauty, but for survival, and yet, the result is beautiful. Pause with that thought, that something so elegant could emerge from something so practical, that a flower, by simply following a mathematical rule, creates art, but it goes deeper. Look at a nautilus shell, or the spiral of a hurricane, or the halls of your fingerprint. you'll see curves that mirror the golden spiral, a close relative of the Fibonacci sequence. It's not just a curve, it's a proportion. The golden ratio, roughly 1.618, is what you get when you divide one Fibonacci number by the one before it. As the sequence goes on, this ratio appears in art, in architecture, in design, and in nature. The branching of trees, the veins in leaves, even the proportions of the human body, all echo this ratio. Why does nature return to it so often? Some scientists suggest it's an evolutionary advantage. Branching in trees that follows Fibonacci rules allows for maximum sunlight exposure. The spiral of a seashell, growing with the golden ratio, allows it to expand without changing shape. Growth, efficiency, balance, all hidden in these numbers. Others see something deeper, a kind of universal order, that beneath the seeming randomness of the world, there's a code, a quiet hum of numbers guiding how life unfolds. Even inside you, in the lungs, the bronchial branches split and divide following ratios reminiscent of Fibonacci. The pattern helps maximize surface area for breathing. Even your heartbeat, when analyzed over time, shows subtle rhythms that flicker with Fibonacci-like intervals. So when you breathe in and breathe out, you're following, in some small way, the same pattern as a spiral galaxy. Let that thought wash over you, that you, a conscious being, are built from the same mathematical language as flowers and storms, that the Fibonacci sequence connects the smallest leaf to the largest galaxy. It's a reminder that the line between nature and mathematics is not a boundary, it's a bridge. And what's more mysterious is that this pattern was known long before modern science. Ancient Hindu scholars described similar sequences in poetic meter. In the 13th century, Leonardo of Pisa, known as Fibonacci, brought it to Europe through a problem about rabbit populations. From poetry to agriculture, the numbers quietly spread, like the pattern itself. They were not invented, they were discovered, revealed, like a fingerprint left by something older than time, something not random, but recursive. And now, when you see a pine cone or a sunflower, you'll know, this is not just a plant, it is a living equation, a curve carved into life by necessity, refined by time, expressed as beauty. It's strange, isn't it, that something as abstract as a number could manifest in petals and waves and breath. That math so often seen as cold or mechanical, is in truth a signature of life, and in that we might find comfort, because it means we are not strangers in this world. We belong to its rhythm, we emerge from its ratios, we are not outside of nature's order, we are that order, expressed in thought and flesh. Picture a coin. Simple, small, one side heads, the other tails. You flip it into the air, it spins, catches light and falls, landing heads or tails. But what does that actually mean? You might say it's 50/50ths, pure chance, a fair toss, an even probability. But even in that simple act, the flip of a coin, the universe whispers in mathematics, because chance, it turns out, is more complicated than it seems. Let's slow things down. A coin toss feels random, yes, but it's governed by physics. The force of your thumb, the height of the toss, the spin, the air resistance, even the softness of the surface it lands on. If you could measure all those variables precisely, some argue, the outcome wouldn't be random at all, it would be deterministic. But we can't measure perfectly, so we rely on probability, the mathematics of uncertainty. Probability gives us a language for the unknown, a way to talk about likelihood when certainty escapes us. Whether it's a coin, a card, or the chance of rain, we reach for numbers to grasp the fog. It begins with something called classical probability. When all outcomes are equally likely, the probability of one outcome is 1 divided by the number of possibilities. For a coin, 1 in 2. For a die, 1 in 6. But life rarely gives us perfect coins, or perfect balance, and this is where things get strange. Imagine you flip a coin 100 times, you get 52 heads. You might shrug, close enough. But what if you got 90 heads, or 10? Something inside you would stir. You'd feel the tug of Bayesian reasoning, the idea that we constantly update our beliefs based on evidence. You might think, maybe the coin is weighted, and just like that, you're doing Bayesian math, adjusting your probabilities based on new information. It's not about one toss, it's about the pattern, the accumulation of outcomes, the signal inside the noise. Take a moment here. Feel that subtle shift from randomness to reason. This is the essence of how we make sense of chaos. We live in a world of incomplete information, so our minds, consciously or not, begin to model uncertainty, to form expectations, to weigh odds, and this process isn't just theoretical, it's biological. Neuroscientists have found that the human brain processes decisions using probabilistic models, from eye movements to language to social judgment. We don't operate on fixed rules, we operate on likelihoods. Our neurons literally compute expectations and adjust them as we gather more input. In other words, you are a probability engine, and so is everything around you: weather, genetics, finance, medicine, even love. All of it dances to the tune of chance. We roll the dice every day without realizing it. But randomness itself isn't chaos. In fact, in the heart of randomness there are patterns. Look at stochastic systems, systems influenced by randomness but still producing structure, like the stock market, or traffic patterns, or rainfall. They seem erratic, but over time they form distributions, bell curves, spikes, long tails. Mathematics gives us tools, like the normal distribution, to understand what might otherwise feel senseless. It's comforting, in a strange way. Even in the roll of dice, there is shape. Even in randomness, there is expectation. But then we encounter true uncertainty, the realm of quantum mechanics. At the subatomic level, particles don't behave in deterministic ways. They exist in probability clouds, states of potential, rather than position. Only when measured do they collapse into a fixed point. Before that, they are waves of possibility. Imagine that. Even the tiniest pieces of the universe exist not as things, but as likelihoods. This is where the coin toss becomes cosmic. Because it's not just about heads or tails anymore. It's about a world where everything, from particles to choices, may be governed by probabilistic laws, and yet, we build meaning on top of this. We make decisions, we take chances, we form habits, tell stories, pursue goals, all on the back of uncertain outcomes. That's the paradox of life. We crave certainty in an uncertain world, but perhaps that's where the beauty lies. Probability reminds us that we don't need to control everything, that randomness isn't our enemy, it's the canvas upon which we paint intention. Take another slow breath. The next time you flip a coin, or face a choice, pause. Let the uncertainty be part of the process. Let it be not a threat, but a companion. Because life, like the coin, turns in the air, spins on forces we can't always predict, but it always lands somewhere, and in that landing, that moment of resolution, we find ourselves. Think of a memory. Not just any memory, but the first one that floats to the surface. Maybe it's a warm kitchen, a laugh from someone long gone, a sudden vivid image of light through a window, or the feeling of rain on your skin. Now ask yourself, why did that memory come back, and not another? Memory feels emotional, personal, like it follows no rules. But beneath the surface, memory is shaped, curated, even by patterns. And those patterns can be described with mathematics. It begins with something called the forgetting curve, a principle discovered in the late 19th century by a German psychologist named Hermann Ebbinghaus. He found that memory doesn't fade in a straight line. Instead, we forget most of what we learn quickly, within hours or days, and then the rate of forgetting slows down. This drop-off isn't linear, it follows an exponential decay curve. Imagine a steep hill at first, then a long, slow slope. That's your brain, letting go. But here's the twist: repetition bends the curve. Every time you revisit a piece of information, the curve resets and decays more slowly. This is the math behind spaced repetition, the most effective method for remembering long-term. It's why flashcard systems like Anki work, and why you can still sing songs from childhood, but forget a phone number in seconds. In other words, when you remember something depends on when, and how often, you forget it. But memory isn't just about practice, it's also about patterns of significance. Studies show that your brain tends to store things that are unusual, emotional, or connected to a story. These patterns aren't random, they align with a kind of cognitive compression algorithm. Your brain is constantly sorting information. What's worth keeping? What's noise? It behaves in some ways like a data scientist, searching for signal in the chaos. Take a moment to reflect on that. In every moment, your mind is performing triage, prioritizing one sensation over another, choosing unconsciously what becomes part of your story. This is why you might remember the exact shape of the clouds on a strange, sad day, but forget what you ate for breakfast yesterday. Your brain isn't recording life like a camera. It's sculpting it, condensing experiences into highlights, patterns, spikes of meaning. using models that resemble statistical filtering. In fact, the distribution of your memories, how often you recall recent events versus distant ones, follows something similar to a power law. You remember recent things often, and distant things occasionally, but both follow a curved slope of mental access. This law, found in fields like linguistics, network theory, and even internet traffic, seems to apply to how we mentally file time. There's another strange pattern too, something called serial position effect. If you're given a list of words, you're most likely to remember the first few and the last few. The middle tends to disappear. This is why beginnings and endings stay with us, in stories, relationships, and moments. The math of memory prefers edges, and here's something even more surprising. Your memory is deeply influenced by prediction errors, moments when your expectations are violated. When something surprising or confusing happens, your brain flags it. These spikes in neural activity encode the moment more powerfully. From a mathematical perspective, the brain is modeling probabilities, and when something breaks the pattern, it gets stored more deeply. So in a way, your memories are a collection of statistical anomalies, outliers, surprises, the data that didn't fit the model. That's why trauma can etch itself so deeply into the mind. And it's also why joy can feel timeless. Those rare shining spikes of emotional energy become keystones in your mental landscape. It's humbling, isn't it, to realize that what you call your life is actually a sample, a curated non-linear collection of remembered peaks and shadows, a dataset shaped by frequency, emotion, and error. And yet, there's something poetic about it. Memory, for all its quirks and losses, gives shape to who you are. It lets you learn, grow, imagine. It makes you more than a machine. And though its structure is mathematical, its meaning is emotional. So maybe the beauty lies not in perfect recall, but in the shape of what we forget. Let that idea settle with you for a moment. Your mind isn't a vault, it's a living system. And like any system, it follows patterns, rhythms, ratios, curves that bend and rise, equations that whisper behind the curtain. You open your eyes and take in the world. Instantly, without effort, your brain constructs space, depth, color, motion. A stream of images stitched together so seamlessly, you hardly notice it happening. But sometimes, the illusion slips. A line looks crooked when it isn't. A circle seems to move even when it's still. Your eyes deceive you, and yet, it's not a failure, it's a clue, a soft whisper from your brain, revealing that perception isn't passive. It's an active construction, built with assumptions, shortcuts, and surprisingly, mathematics. Consider the Muller-Lyer illusion. Two straight lines, identical in length, one with arrow tails pointing inward, the other outward. One looks longer, unmistakably so, even though they're the same. Why? Because your brain interprets the angles as depth cues. It assumes a 3D world, even when shown a 2D image. The mind uses geometry to estimate space, and in doing so, it guesses wrong. Take the Ames room, a distorted room that, from one angle, looks completely ordinary. Two people stand on opposite sides. One appears huge, the other tiny. But step into the room, and the truth emerges. The floor slopes, the walls lean, the angles lie. It's all about perspective geometry, how parallel lines and shapes are manipulated to fool your sense of scale. Even the famous rotating snakes illusion, those concentric rings that appear to move, use tiny shifts in brightness, edge contrast, and angular geometry to trick your brain's motion detectors. The illusion lives not in the image, but in the mathematical timing of how your brain processes contrast and light. What's astonishing is that these tricks don't just work sometimes, they work consistently, across cultures, ages, even species. Certain illusions even fool birds and primates, suggesting the underlying math is universal. It's not about what we've learned, it's about how we're wired. Take a moment to reflect on that. Your perception of reality, what feels solid, visual, obvious, is actually a predictive model, one the brain builds using internal equations. When the visual input doesn't align with those predictions, the model breaks. And in that break, we glimpse the system beneath. One of the most beautiful illusions is the cafe wall illusion, a pattern where straight horizontal lines appear to be slanted. The secret lies in how our brains detect edges. The offset of black and white tiles tricks our visual cortex into misjudging alignment. And once again it comes down to pattern recognition, the brain applying algorithms for what it expects to see. This raises a fascinating idea. We don't see the world as it is, we see it as the brain calculates it to be. Every second, your brain is solving problems of geometry, proportion, contrast, depth, and light, using mathematical heuristics that have evolved over millions of years. You don't just look, you compute. But here's where it gets truly mind-bending. Some illusions exploit non-Euclidean geometry, spaces where traditional rules of distance and shape don't apply. Imagine a triangle with 3 right angles. It shouldn't be possible unless you're on a curved surface, like a sphere. Some visual illusions are built this way, subtly curving or bending perceived space to create impossible figures. Your brain, trying to force flat logic onto a bent reality, gets confused. And yet, that confusion is beautiful, because it means our perception is flexible. It's not rigid math, it's adaptive math. It works most of the time, but when it breaks, it teaches us something profound, that what we call reality is partly an invention. Even in art, illusions reveal deeper truths. M.C. Escher, the Dutch graphic artist, used impossible geometry to show waterfalls that flow uphill, staircases that loop forever, and objects that exist in visual paradox. He wasn't just playing, he was expressing mathematical ideas. Concepts like recursion, symmetry, and the infinite, all through images that the brain tries and fails to resolve. Let that settle in for a moment. Your brain wants the world to make sense. It tries to flatten space, straighten lines, fill in gaps, assign shadows. But when it's presented with something mathematically inconsistent, like an impossible cube or an endless spiral, it stalls, it stares. And in that moment, you experience a kind of wonder, a friction between logic and perception. And perhaps that's what makes illusions so powerful, not just that they deceive us, but that they reveal us. They show that we are pattern-seeking creatures, relying on internal models, that we don't just absorb the world, we shape it through expectation and approximation. And those approximations, while usually accurate, are built on mathematical rules so deep we're not even aware of them. So the next time you see an optical illusion, take a moment to appreciate what it really is, a mirror held up to your mind, a glimpse of the silent math behind how you see, interpret, and believe. You're walking, not thinking about it, just moving forward, step after step. The sway of your arms, the lift of your heel, the soft roll of your weight from one foot to the other. It feels natural, effortless. But beneath this simple rhythm, something extraordinary is happening, something ancient, something mathematical. You might not notice it, most people never do. But the way you walk often follows a hidden ratio, a silent harmony that echoes throughout nature, architecture, music, and even your own body. It's called the golden ratio. And it appears in the most unexpected places, including your footsteps. The golden ratio, roughly 1.618, is a mathematical proportion known for its balance and beauty. You've seen it in spiral shells, in the petals of flowers, in the layout of galaxies. But it's not just for the natural world. It lives in the proportions of the Parthenon, the structure of famous paintings, even in the layout of credit cards and computer screens. So what does it have to do with the way you walk? Researchers studying human gait, the way we move, have discovered something remarkable. The length of your stride, the swing of your leg, the timing between each step, often conforms to proportions that approach the golden ratio. Not by conscious choice, not because we're trained to do it, but because it's the most efficient way to move. Think of your legs as pendulums, each one swinging forward and back. If your steps are too short, you waste energy. If they're too long, your balance falters. But when your stride length and timing fall into this golden proportion, not equal, but elegantly offset, your body uses less energy. It flows. It's a kind of mathematical optimization. Evolution, through millions of years, found a solution that balances speed, stability, and effort. The result, your natural gait, this ordinary act of walking, turns out to be an unconscious act of geometry. But it goes deeper than that. Not only do our movements reflect golden ratio timing, but so do our limbs. The length of your forearm to your hand, your thigh to your calf, even the position of your navel. Many of these proportions tend to hover near 1.618. Not perfectly, of course. Bodies are messy, but the tendency is there. Again and again. Why does this matter? Because it means your very structure, the scaffolding of your body, might be tuned for golden movement, for a rhythm that mirrors the same ratio we see in sunflowers and spiral galaxies. That's not just poetic, it's profound. It suggests that mathematics doesn't just describe the world, it builds it. Take a moment and feel it. The next time you walk, even just across a room, notice the rhythm, feel the pendulum of your arms, the rise and fall of each step. It's not rigid, it's not exact, but it flows, and flow is key. Flow is what the golden ratio offers. It isn't a rule, it's a tendency toward grace, toward balance, and your body, without needing to think, often follows it. Some dancers and athletes train specifically with this in mind. Movements that adhere to golden timing are often perceived as more beautiful, more natural. There's even research suggesting that audiences prefer choreography and athletic performance that reflect golden proportions, even if they don't know why. It's not just what we do, it's how we feel it. But there's something else to reflect on here. You didn't have to study math to walk this way. You don't need to measure your limbs or calculate your cadence. You just move. And in that movement is a quiet expression of something ancient, something shared between humans and flowers and waves and stars. That's what's so comforting about this idea. The golden ratio isn't just a number, it's a pattern that emerges when systems, biological, natural, creative, find harmony. It's not imposed from the outside, it grows from within, and perhaps that's why it shows up in so many places. It's not that the world is designed according to math, it's that math is the language of how the world designs itself. Your walk, then, isn't just a method of getting from place to place, it's a small act of beauty, of balance, of unconscious participation in the elegance of the universe. So the next time you walk under trees or across tiles or down a quiet street, think of this: you're carrying a spiral with you, not one that spins but one that steps, that flows, that follows an invisible ratio through time and space. Listen, not to the world around you, but to the soft, persistent rhythm inside your chest. Your heartbeat, thump, thump, a steady companion, constant, predictable. But what if I told you it's not? What we think of as a steady heartbeat is actually full of variation, minute shifts, delicate changes in spacing between each beat. And if you zoom in mathematically, you'll find that this rhythm, the very sound of life itself, follows a hidden structure, one that isn't regular, but also isn't random. It's fractal. Fractals are patterns that repeat at different scales. Zoom in, and you see the same complexity you saw from afar. Think of the branching of trees, the curl of a fern, or the jagged edge of a coastline. No matter how closely you look, the pattern continues. Now imagine applying that idea to your heartbeat. Doctors and scientists once believed that the healthiest heart was one that beat in a steady, predictable rhythm like a metronome. But they've discovered the opposite is true. A truly healthy heart displays a kind of structured variability. The time between beats, known as heart rate variability, changes constantly in subtle, intricate ways. These variations follow fractal patterns. And here's the strange part: these patterns are not random. They reflect the balance of your nervous system, how your body adapts to the world, how it responds to stress, rest, and emotion. In fact, when a person is under deep stress or close to death, the heart becomes too regular, too mechanical. It loses its complexity. It loses its adaptability. So paradoxically, your life depends on irregularity, a controlled chaos pulsing in your chest. This idea that chaos can be healthy is counterintuitive. It challenges our desire for order and predictability. We like to think of the heart as a drum, but it's more like a jazz musician, improvising, adjusting, flowing with countless invisible factors. Take a moment to reflect on that. Right now, as you lie still, maybe preparing for sleep, your heart is playing a silent fractal song. Not perfect, not mechanical, but beautifully adaptive, responsive to breath, to emotion, to the world just beyond your skin. The mathematics behind this are complex, but the metaphor is simple. Your body is a dynamic system. It resists stillness. It craves movement, even in its rhythms. Researchers use something called nonlinear dynamics to study this. It's a mathematical way of describing systems that don't follow a straight line, that twist and loop and evolve in unexpected ways. Your heartbeat is one of these systems. It has memory. It has sensitivity. Tiny changes can ripple into large effects, like a kind of biological butterfly effect. It's also tied to something called 1F noise, a pattern found not just in heartbeats, but in music, brainwaves, weather patterns, and even traffic. It's a balance between complete randomness and complete order, a middle space, a living rhythm. That middle space is where life thrives, and perhaps that's where meaning thrives too. In things that are neither perfectly controlled nor totally chaotic, in systems that feel alive because they bend and breathe. It's strange to think of your heartbeat, something so familiar, so automatic, as a kind of equation, but that's what it is, a living formula, solving itself moment by moment, adapting to every whisper of change inside and around you. It's not something to control, it's something to listen to. There's a meditative quality to that. A comfort in knowing that your body is doing something so intricate, so intelligent, without any effort from you. You don't have to command your heartbeat to follow a fractal path. It simply does, because life is made that way. And this pattern, this quiet geometry of being, reminds us that math isn't sterile, it isn't cold, it's intimate. It shapes the pulse of who you are. So the next time you feel your heartbeat, maybe after a moment of fear, or joy, or calm, try to hear the deeper pattern, the invisible fractals, the wild intelligence of your body keeping time. And now, let that rhythm guide us forward, away from the biology of the body and into the flow of the body in motion, because the way you walk, the swing of your arms, the stretch of your legs, the timing of your steps, might also be shaped by a mathematical code. You're standing in line at the grocery store. Maybe it's late. The hum of fluorescent lights surrounds you. There's soft chatter in the background, maybe distant music. You glance at the shelves near the checkout. Gum, candy, magazines, batteries. Small things, easy choices. And then you notice something else. The prices. $2.99, odd numbers. Always just below something whole. It's not an accident. These numbers have been chosen, not just by accountants, but by psychologists, marketers, and data scientists. Because the numbers you see shape how you think. We often assume that we're rational, that we see a price and simply judge whether it's fair. But in reality, our brains are doing something more subtle, something mathematical, and the people behind product pricing know that. This is called left-digit bias, a quirk in human cognition. When we see $4.99, our brains process it as 4 something, not 5. Even though it's just 1 cent different from $5, that tiny shift in perception, not value, changes how we feel about it. Our brains weigh the first digit most heavily, often ignoring what comes after the decimal. We round down emotionally, even when the math says otherwise. It's the same reason why clearance items are priced at $1.97 back. The odd endings suggest a calculated discount, something intentional, engineered. This isn't just random, it's a signal, a cue that whispers, this is a deal, even if it isn't. You've probably also seen offers like 3 for $5 or buy one get one 50% off. These are anchored in a different kind of math, reference pricing. Here your brain is being given a suggested normal value. You see the first price and everything else is compared to it. This is called anchoring, a cognitive bias where we rely too heavily on the first piece of information we're given. A $40 bottle of wine seems overpriced until you see it next to a $70 one. Suddenly, it feels like a bargain. Stores use these tricks or strategies depending on your point of view because they work. Studies have shown that small changes in how a price is written can have a measurable impact on what people buy, how quickly they decide, and how satisfied they feel afterward. Even the font and placement of numbers matters. A price written in a smaller font looks cheaper. A price without a dollar sign feels less serious. If the price is to the right of the item, we subconsciously associate it with something more distant or abstract. If it's close to the product, snug beside it, we feel like the price is part of the item itself. Take a moment to reflect on that. Just numbers on a tag, right? But those digits, their size, shape, position, are manipulating your sense of value, subtly, gently, mathematically. And this isn't just about sales, it's about how we think with numbers, even when we don't realize we're doing it. The way we estimate, compare, choose, it's all influenced by mental shortcuts, shaped by evolution, culture, and yes, marketing. Our brains weren't designed for price tags. They evolved to make fast judgments in a complex world, to spot threats, to estimate distance, to recognize patterns in leaves and footsteps. The fact that those same instincts now get triggered by cereal boxes and discount signs is, in a way, a misfiring. A side effect of mathematical intuition being used in an artificial environment, but that doesn't make it any less fascinating. It means every trip to the store is, beneath the surface, a subtle dance of probability, comparison, and value perception, a kind of low-level numerical hypnosis. Even the layout of stores is designed with math in mind. The most expensive items are at eye level, the cheaper ones are down low, where fewer people look. End caps, the displays at the end of aisles, are statistically more likely to convert sales. Why? Because we're more likely to pause there. It's a numbers game of flow, timing, and behavior. So the next time you're holding a product, debating between $3.99 and $4.29, ask yourself, is this really about the price? Or is it about the way my brain is interpreting the number? What am I comparing it to, and who put that comparison there? There's a kind of invisible architecture beneath your decisions, a framework of small nudges, subtle equations, hidden assumptions, and it's not meant to deceive, it's meant to guide, but it's still math. Quiet, influential math that shapes how you live your life, one tiny decision at a time. And if something as ordinary as shopping contains this many hidden calculations, what else might be governed by numbers? Picture yourself walking through a forest. The ground is soft, and the light filters down in golden beams. The air smells of pine and soil. You look up, and for a moment you notice the pattern of the branches, how they spread, how they never seem to collide. The leaves don't stack on top of each other, they spiral outward, evenly spaced, drinking in light without waste. It feels intentional, like a kind of wisdom coded into the tree itself. But this is more than just natural efficiency, it's mathematics. Specifically the Fibonacci sequence, a quiet number pattern that shows up in some of the most surprising places. The sequence begins simply, 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on. Each number is the sum of the two before it. But what makes this sequence truly special is how often it appears in the structure of living things, not by design but by necessity. Look closely at a pine cone, or the spiral of seeds on a sunflower, or the way leaves grow around a stem. In many plants, leaves sprout at Fibonacci intervals, turning around the stem by roughly 137.5 degrees each time. Why? Because this angle, known as the golden angle, results in the most efficient way to space things out. It minimizes overlap and maximizes exposure to sunlight and rain. It's not just beautiful, it's functional. Evolution somehow found a solution that also happens to be mathematically profound. That number 137.5 degrees is tied to the golden ratio, approximately 1.618. This ratio appears when you divide two consecutive Fibonacci numbers, say 21 divided by 13. As the numbers grow, the ratio between them approaches that golden constant more and more closely. Artists have used this ratio for centuries to design pleasing compositions, but nature used it first. It's as if trees and flowers instinctively know the secret language of numbers, but they don't know in the conscious sense. They express it because it works, because this is the shape of survival. Even the scales of pineapples, the petals of daisies, and the spiral shells of nautiluses obey Fibonacci. In fact, you can walk through an entire forest and spot these patterns again and again, not in artificial perfect lines, but in flowing organic spirals, beautiful in their irregularities. There's something poetic about that living things, which feel so spontaneous, so chaotic, are also following an ancient pattern. It makes you wonder if nature at its core is trying to solve problems of space, of light, of growth, using the same logic we humans try to grasp with numbers and theory. And there's something humbling about it too. Long before Fibonacci wrote down his famous sequence in 1202, long before humans even understood what a number was, plants were growing this way, spiraling, counting, not with symbols or arithmetic, but with structure and rhythm. Life itself was doing math, silently, invisibly, perfectly. Take a moment to reflect on that. The leaf that just fell beside your foot may have grown at exactly 137.5 degrees from the one before it. The branch above your head may be extending in the 5th or 8th Fibonacci layer of the tree's growth, and you're just walking underneath it, unaware until now of the deep order around you. These aren't just natural curiosities, they're a kind of blueprint, a way of understanding that perhaps everything, even the things that seem wild, follows hidden logic. It raises questions, doesn't it? If plants grow this way by default, what else in our world or in ourselves follows mathematical rules we haven't yet recognized? Are we just another expression of the same equations? And yet there's comfort in that idea, in the thought that beauty isn't random, that form and function, nature and numbers, are not separate, but intertwined. It suggests that the universe isn't just functional, it's elegant. As you continue your walk, try looking again at the branches, the petals, the spacing of leaves, the spiral of a fern, the cone of a cedar tree. You're not just seeing a plant, you're seeing an algorithm, a silent intelligence older than language, a recurring theme in nature's design, expressed without words but perfectly understood by the world around it. And so we leave the forest behind, carrying with us this newfound awareness that numbers don't only live in textbooks, they live in sunlight and leaves, in seeds and stems. That math is not an invention, it's a discovery, one nature made long before we did. Imagine waking up slowly. The world is still quiet. You shuffle into the kitchen, half asleep, and reach for your mug. Maybe it's chipped at the rim. Maybe it's your favorite. You pour in the water, add your coffee or tea, and stir gently. You might not realize it, but in that quiet, swirling moment, you've just summoned one of nature's most ancient and universal patterns, a pattern that physicists and mathematicians have spent centuries trying to describe. As the liquid spirals, you see motion. But what you're really watching is geometry in motion, a vortex, a whirlpool of particles shaped by invisible laws. These aren't just visual effects. They're the fingerprints of equations embedded in the very fabric of reality, and they're all around us, especially in the most ordinary moments. The way your coffee spins is governed by fluid dynamics, the mathematics of how liquids flow. The very act of stirring sets off a cascade of variables: angular momentum, viscosity, centrifugal force, even the speed of your hand matters. Mathematicians have tried to model this with equations called the Navier-Stokes equations, some of the most complex and unresolved formulas in science. In fact, solving these equations in general cases is so difficult, the Clay Mathematics Institute has offered $1 million prize to anyone who can. But despite the complexity, your coffee obeys these rules effortlessly. When you stir, the liquid doesn't move randomly. It forms nested circles, like mini spirals winding toward a center. This is called laminar flow, where liquid layers slide smoothly over each other. But stir fast enough, and chaos emerges. The spiral breaks down, forming turbulence, unpredictable, almost wild. Yet even turbulence follows deeper patterns, ones we don't yet fully understand. You might notice another thing if you watch closely. Add milk or cream, and it doesn't just dissolve instantly. It curls inward in elegant tendrils, like storm systems on a weather map. This is called diffusion, the process by which particles spread from areas of high concentration to low. It's mathematics again, quietly painting spirals in your cup. Now pause for a moment and think about that. Even in something as small and personal as a cup of coffee, there are invisible systems shaping what you see. Physics, equations, ancient logic that predates human consciousness. And yet you don't need to understand any of it to witness its beauty. The mathematics simply unfolds, indifferent to your attention. Take a moment to reflect on this. In a single quiet moment of your day, one that feels entirely yours, you're witnessing universal laws. It's easy to think of math as something confined to chalkboards, textbooks, or classrooms, but in reality it's the operating system of the universe, and it's always running, even in your hands. This hidden math goes beyond your mug. Similar patterns appear in galaxies, hurricanes, and black holes. The spiral you see in your cup is the same geometry used by nature to shape the universe, known as logarithmic spirals. They never quite reach the center, they just keep turning inward. There's something hauntingly beautiful about that, the idea that even chaos is shaped by rules we can almost understand but never fully tame, and maybe that's part of the appeal, that comfort in knowing there's order beneath the noise. That something as simple as stirring a drink can place you in direct contact with the fabric of nature. It's easy to overlook moments like these. They feel too small, too routine. But the math doesn't care if you're paying attention. It continues unfolding quietly, patiently, like a whisper in the background. The kind of whisper that only becomes audible when the world slows down. As your drink settles, the spirals fade, the motion dissolves, but the math remains, hidden, dormant, ready to reappear at your next sip, your next stir, your next moment of quiet. And as you place your mug down and move through the rest of your day, remember, this moment wasn't empty, it wasn't mundane, it was a window, a small one, yes, but through it, you saw a pattern shared with stars, oceans, and clouds. So as we leave behind the spiral of your coffee, let's keep traveling. What other secret codes are hiding in your everyday life? Where else does math speak softly, just under the surface? Think about your bedroom right now. The rumpled sheets, a pair of socks that didn't quite make it to the laundry basket, a half-empty glass on the nightstand, maybe a book face down where you left it last night. It's not chaotic, exactly, but it's not perfect either. It's lived in, a quiet reflection of you. What if I told you that this state, this gentle drift from order to disorder, is not laziness or forgetfulness, but the inevitable pull of entropy? Entropy is one of the most misunderstood and most profound ideas in all of science. It touches physics, information, psychology, and even the slow unraveling of everyday life. So tonight, let's sink into it. Let's talk about the entropy of your bedroom and what it quietly reveals about the universe itself. At its core, entropy is a measure of disorder, or more precisely, the number of ways a system can be arranged without changing its overall structure. Imagine a freshly made bed. Sheets tucked, pillows fluffed, everything symmetrical. There are only a few very specific ways a bed can be that tidy, but there are countless ways for it to become messy. A toss, a turn, a duvet kicked to one side. You don't have to try to mess it up, it just happens. That's entropy. Order gives way to disorder, not because disorder is special, but because it's more likely. In physics, this idea is encoded in the second law of thermodynamics, which tells us that in a closed system, entropy always increases over time. Left alone, systems drift toward chaos. Ice melts, coffee cools, sandcastles crumble, and bedrooms, they get messy. What's haunting and beautiful is that entropy isn't just about things falling apart, it's about probability. There are billions of microscopic ways a room can be untidy, but only a few ways for it to look perfectly clean. So the universe, following its own rules, tends to choose the messy route. And this isn't just philosophy, it's math. Entropy is deeply rooted in statistical mechanics, a field pioneered by Ludwig Boltzmann in the 19th century. Boltzmann understood that thermodynamics, the study of heat, energy, and work, could be described in terms of atoms and molecules behaving randomly. In simpler terms, the more ways a system can be arranged, the higher its entropy. So, your bedroom, seen through this lens, is not just a space, it's a thermodynamic system, slowly exploring more and more configurations, and every time you drop your clothes on the floor, or let the books pile up, you're not breaking the rules, you're following them. But here's the twist. You, the human in the room, are a machine that fights entropy. You clean, you fold, you align and arrange. You create pockets of order in a universe that leans toward disorder. This act of tidying up is more than just habit. It's a small, stubborn defiance of the cosmic trend, powered by energy, will, and a deep evolutionary need for structure. Still, you're not truly stopping entropy. You're just moving it around. Cleaning your room takes effort. Calories burned, muscles moved, brain power used. That energy dissipates as heat. The universe as a whole becomes slightly more disordered, even as your bedroom becomes cleaner. That's the catch. Local order increases global entropy. In a way, every act of tidying is a kind of cosmic magic trick. The neat desk, the made bed, the organized bookshelf, they're temporary illusions held together by your energy and attention. Without you, they fade. Dust settles, books scatter, the bed wrinkles again. And yet, there's comfort in that. Because entropy isn't malevolent. It's not chaos for chaos' sake. It's simply possibility expanding. It's the reason time flows forward and not backward. It's the gentle slope on which reality glides from past to future. It's why you remember yesterday, and not tomorrow. And it's why your room feels different in the morning light than it did before you fell asleep. There's something oddly soothing in realizing this. That disorder is natural. That imperfection isn't failure. It's physics. Take a moment to breathe that in. Your scattered socks, your half-folded laundry. They're not signs of neglect. They're signs of a living, breathing system in motion. A room that evolves. A tiny entropy engine nestled inside a spinning planet that itself drifts toward thermodynamic equilibrium. Now, let that be your permission to rest. You don't have to fix it all tonight. You can leave a little entropy behind, because in the vast tapestry of existence, you are a temporary architect of order, carving shape from chaos, moment by moment, then letting it go. So as you drift into sleep, remember, entropy isn't the enemy. It's the heartbeat of the universe, and your bedroom, no matter how messy or clean, is simply part of the story.